I'm going to talk a little bit about SAT solvers and how they run. I don't want to assume that you know what a SAT solver is, but even before I start describing how SAT solvers run, let me try and describe one particular problem which was solved using SAT solvers. So here's the question. Partition the set of numbers 1 to, let's say, 10. Okay, so let's call this, let's denote this in this way. Okay, so partition this into two sets. Let's call the two sets red and blue. Such that neither of these two sets contains what we are going to call a Pythagorean triple. So did you hear a lot about Pythagorean triples in the previous talk? No, not at all. Okay, but you know what a Pythagorean triple is? Three numbers a, b, c such that a square plus b square is equal to c squares. Okay, so any such triple is a Pythagorean triple. You just want to partition the numbers 1 to 10 into two sets. How would you do this? There's more than one way of doing this. So we can just start constructing, like, let's put 1 here, 2 here. So I'm constructing the red set, 4, and then you realize, okay, 5 cannot go into this set. So then that goes into the blue set, 5. Now 6, there's no clear reason where it can go. So let's put 6 here. Let's put 7 here. Can continue, 8, 9, but now you can't put 10 there. So you have to move 10 here, right? Okay, so this would be a partition, and this is fine. Okay, so now let me change the question. Partition 1 to 20. You can extend this partition, do a little bit more. I mean, put the remaining numbers, So we have already put 10 here, you put 11. Maybe at this point you see that it would be useful to have somewhere a list of Pythagorean triples. So what are the Pythagorean triples up to this point? You have 3, 4, 5, we had 6, 8, 10. These already you had to split. Now because we are going up to 20, there are a few more. There's 5, 12, 13, so you have to be a bit careful about where this goes. There's 9, 12, 15. There's 8, 15, 17, and there should be one more, right? 12, 16, 20. I guess if you go up to 20, then there are these. You have to avoid these. You can split this. So, okay, you stare at it a little bit longer and you can do this split also. So now let's up the game. Partition 1 to 100. You can presumably write a program. At this point you don't want to sit and write all the triples that are there and make sure that you split them nicely into two sets. So maybe, you are all here for the computing Olympiad, so you know how to write code which will fatafat do these things. List out the Pythagorean triples up to these numbers. Write a program which tries out partitions. How many partitions does it have to try out? There are 100 numbers. You have to put them into two sets. There are 2 raised to 99 ways of doing this, right? There are 2 raised to 100 subsets, but each subset red, the remaining subset is blue. So actually each pair gets represented twice, so 2 raised to 99 ways. You're not going to write a program which tries out 2 raised to 99 ways. Even if you don't explicitly count steps like this, by now you have a good enough feeling 2 raised to 99 is a pretty large number. So you'll want to do something smarter. But it turns out that 1 to 100, it's not that difficult to find the partition. It's just because these are small numbers. We can list out the triples explicitly, and there are not too many constraints. So let's go even further. 1,000, 10,000. Okay. Given a number n, just partition the numbers 1 to n into this red and blue set. How are you going to do this? So what kind of programming tricks could you use? That's the question which I want you to think about. So it seems pretty clear already at 100, I think you all agreed that brute force is not the answer. So you need a trick. You need some clever algorithmic trick to do this. And now we want to go way beyond 100, 1,000, 10,000. Of course, even at 100, very quickly you said that there are 2 raised to 99 ways, and it is true that there are 2 raised to 99 ways. But the number of constraints is much fewer. Every triple is giving you a constraint. This triple should not be entirely red, it should not be entirely blue. And the number of triples is much less. Even if you go all the way up to 100, how many Pythagorean triples are there? Maybe some 20 odd, not too large a number. So there should be some good way of using this fact that the number of triples is sparse, and then trying to search for something that meets these constraints. But maybe at this point you should think a little bit more. I mean, there's this algorithmic task, partition these numbers. But how do you even know that you can do this? So this looks like just a mathematical problem, right? Find a partition. So if it's a mathematical problem, there should be a mathematical solution which is not even algorithmic. Okay? Just prove first that there exists such a partition. And then you try to write out a proof that such a partition exists. And if you are able to write out such a proof, then depending on the kind of proof you have written, you may be able to translate to an algorithm or you may not. So a proof does not guarantee that you will get an algorithm, but there's a good chance it might. So maybe first you should try to get a proof. Okay? Proof that such a partition always exists for 1,000, for 10,000. Well, for small numbers, you can prove that it exists by giving the partition. Once the partition is given, checking that it is indeed a partition is easy. But for larger numbers, now the question is, how do you come up with this partition? So, okay, so that's our next question. Does such a partition always exist? What exist meaning, I mean for every n. You want to partition the numbers from 1 to capital N, does the partition always exist? And so if the answer is yes, then convert a proof to a partition. So for a particular n, if a partition exists, convert a proof that a partition exists to an actual partition. And if the answer is no, then you're kind of stuck. You need to know how to prove that the answer is no. Then after that, you're no longer stuck, because then your job is clear. There is no such partition, you don't need to find it. So it turns out that this question was posed some 100 years ago. Maybe it must have been posed even earlier, but 100 years ago it got some attention. Okay? Is it true that for every n, you can partition the numbers 1 to n into these two red and blue sets, neither of which contains a Pythagorean triple? In fact, the original question was, can the set of natural numbers be partitioned? So n as in natural numbers n. And very recently, 6-7 years ago, it was proven that the answer is no. You were hoping that the answer is yes, and then you could start using your coding ingenuity. Turns out that the answer is no. Okay? So the answer is no. Where does it fail? Well, again, if you say that the answer is no, it's not that it's not possible for every n. Right? I mean, we saw for 10 it's possible, for 20 it's possible. There's some number at which it fails. So smaller numbers than that you can partition, but the moment you include that number, you are not able to do this. How large is that number? How can one find it? So it turns out that this statement fails at a number which is between the last two numbers that I asked you to do. So it fails at 7,825. Okay? I don't know of any great significance of this number, 7825. Okay? All I can tell you is that if you are given the algorithmic task of partitioning the numbers 1 to 7,824, then yes, you can do it. If you are asked to do it for 1 to 7,825, then you can't do it. So how do we know this answer? Okay? So this was a result, like I said, it was from 2016 by 3 researchers, Hewler, Kuhlmann, and Marek. And I mean, they have written a technical paper in which they describe how they proved this. But they've also written some popular science articles explaining what went behind this. And the title of one of their most well-read popular articles, which appeared in Nature, is titled "The Science of Brute Force." Now again, as they used computers. Yes. They created a block. So, of course, the question is asking you to color the numbers, right? You are coloring them red and blue. So, they were trying to create the coloring. And they used it failed at some point, but how do you know that it has failed? I mean, so they call this the science of brute force, but you stop for a moment and you think, what do they mean by brute force? What is the first thing that would come to your mind when you think of brute force? Even at 1,000, forget at 7,000, at 1,000, brute force would suggest to you 2 raised to 999 ways of partitioning, right? So when they say we did this by brute force, do you think that they actually tried out all these ways? 2 raised to 999, no matter how much supercomputing power you have today, we cannot do this. So they called it brute force, but it was, even brute force can be smarter than what we think of as dumb brute force, okay? And they did that. So this is what I want to say, that in an algorithm which is essentially brute force, according to the authors, is not essentially brute force. There's a whole lot of very clever ingenuity behind the algorithm, and that is what we want to look at. Okay? So what did they do? Okay, so let's write a couple of points about their proof. They solved it using computers. Okay? Using very, very heavy computer power. They had access to a massive supercomputer at the University of Texas, Austin. They used it extensively. And you have written code, you have tried to debug it, you know programs often are buggy. Okay, so they solved this using computer. How do we know that what they have solved is correct? No? So do we trust their answer? Of course, they also would have anticipated this question. Why would anybody trust an answer which has been, a computer runs for 2 days, 3 days and says yes, or it says no? It doesn't mean anything. So their program also produced a proof. The proof would presumably be long. Okay? A proof that there is no such partition, one way of proving that there is no such partition is to enumerate all the 2 raised to 999 ways. But there could be other shorter proofs. Right? And their program did produce a proof. That proof was certainly shorter than 2 raised to 999, but it was still pretty long. How long do you think it was? 1 terabyte. Terabyte is how many zeros? Mega, giga, tera. No, pico, tera. Lots of zeros. Okay. So your guess is it was 1 terabyte. Their proof was, yes, you're right, it was in the terabyte range. It was 200 terabytes long. Well, at 200 terabytes, it was still not the complete proof. At 200 terabytes, it was the skeleton of a proof. But this skeleton, it had lines of the proof where filling in the lines was something that could be done fast. So if I give you lines up to now and then I say, okay, here's the next line, it is not something that immediately follows from the previous line, but the work to fill in the gaps, that is something that either a human being or a computer can do very fast. Okay? So for some reason, they did not write out the entire proof. I think there were also limitations on storage, which forced them to do this. Just write down the skeleton. But the skeleton has enough information to pad out into a complete proof efficiently. So the skeleton was 200 terabytes long. Who can check such a long proof? You or I cannot, right? So we are back to the first question. Why do we trust their proof? The proof was computer verified. Which means that there was a different program which could take this skeleton, patch up all the lines in between and verify it. Okay, so let's ask about this verifying program. What kind of a program was this? So the verifying program had to download the proof, reconstruct all the missing lines, and then check that everything worked. So to download, reconstruct, and verify. These 3 things together took, it was of course run on a parallel computer, but if you just add up the CPU time, how many CPU hours do you think it took? 30,000. In 30,000 hours, the proof could be downloaded, the skeleton could be patched up, and then the proof could be verified. Okay, so this was a pretty long computation to verify the proof. In such a long computation, again, there can be errors. Why are we sure that this was correct? So we could, just as we asked this question here, is it correct? We can ask, was the verifier correct? And this is never going to end, right? Like somebody else verifies the verifier, is that person correct? Is that program correct? But now there's a big difference. The program which did this solving is the program that we will talk about. It was a SAT solver. It's a pretty complicated piece of software. Although if you ask many of the people who implement these, they say it's simple. They're like basic tricks. It's not simple, believe me. Okay, there's a lot of very clever tricks going on there. This guy, the verifier, is actually extremely simple. It is so simple that a human being would not even want to do this task. It's one of those mechanical tasks that today we are like just looking for a task that should be offloaded onto a machine to do. It's robotic, it is mechanical, it has no challenge to ingenuity. Okay? Line after line after line is given, fill in the gaps and check whether line 1 plus line 2 gives line 3. Check whether line 3 plus line 7 gives line 9. Some notion of plus or combine or extremely routine mechanical tasks. No human being would want to sit and do it. There is no reason why we should sit and do it. We can write a program to do this, but we can trust that program because that program is so simple. That program does not have complicated recursion. It does not have major loops jumping around here and there, nothing. Such a simple program. So for complicated programs, we could hope that at least we try and check whether this program is correct on this input. You know, a program may be wrong, but fortunately for you, on the input on which you wanted to run it, it ran correctly, and then you get your marks. You are happy. So in the first case, you would be happy with something like that. I mean, you don't know whether the program is right or wrong, but on this input, 7825 or whatever, if it was correct, that's good enough. That's what we want to know. But this verifier program is so small that we can do much better than that. We can formally verify it. So this verifier is extremely compact. It is extremely simple. And therefore, it can be formally verified. So there are formal methods to certify that the program is correct. And here I mean that it is correct on all possible inputs. Okay. So this is a program which has been formally verified. So we have a formally verified checker program which has downloaded this 200 terabyte proof and has filled in all the gaps and has certified that that proof indeed holds. And that is a proof that there is no partition of these numbers. So therefore, now we know the answer to this question, which is the Boolean Pythagorean triple problem, that the natural numbers cannot be partitioned and the numbers 1 to 10,000, 1 to 7825 cannot be partitioned. Okay, good. So now we should be paying more attention to that complicated program. Okay. So let's see, how did they solve this? So how did these three authors use the computer, use computers to solve the Boolean Pythagorean triple problem? Hmm?
They got $100 from MIT for solving this question.
They got $100 from MIT immediately after they solved it. Afterwards, they got a lot more. Not just money, they got a huge amount of free time on the Amazon Web Services cloud computing server. And they have been using it and using these same methods to settle more mathematical problems, which perhaps will become eventually amenable to pure math techniques. But right now, we don't know any way of solving them mathematically, and they have been using computers to solve them. Okay. So what they did was to encode. So let's say that this is BPT. So they encoded BPT, let's say n. Let's say we're trying to solve the Pythagorean triple problem for numbers up to n. So they encoded BPT n as an instance of SAT. And then they used a SAT solver. Okay, so now we want to see what is this encoding into SAT. What do we mean by an encoding into SAT, and what is this SAT solver that they used? So instead of giving you have already heard what is a generic description of the problem SAT in Prajakta's lecture earlier, but here instead I will tell you this instance that arises from here. Okay, so we have these numbers 1 to n which we want to partition. So let me set up variables. I have variables x1, x2, up to xn. And this is the Boolean case. So each of these variables is allowed to take true values, true or false. We are in the Boolean setting, so logical. We are using logical reasoning. I mean, a mathematical proof, which is what we are after, is a proof using logical reasoning. So there are true and false. We are not dealing with actual numbers. So they are all supposed to take values which are either true or false. And For convenience, we may represent true as 1 and false as 0, but this does not matter. Basically, they take only two values, true or false. And just as we say, can the numbers be put into these two sets, we want to now say, can these variables be given values true or false? So let's say that true means that it goes into the red set, and false means that it goes into the blue set. So what we want to ask is, can I assign values true or false to the variables x1 to xn, which is the same as saying, can I put the numbers 1 to n in these buckets, red and blue, such that. So now that such that, how do we say that in the language of SAT? Okay. Now we want to write down the constraints. So for every Pythagorean, so okay, this is, where did the eraser go? Yeah. Okay, I don't know whether you are familiar with this notation. Let me keep it there. This means for all. For all Pythagorean triples of the form ABC, we want to say that ABC go into, they don't all go into the same bucket, right? I have a red bucket and a blue bucket. How do I say that using these variables? So I say that at least one of XA, XB, and XC must be true. They are not all in the false bucket. At least one of them is true. And similarly, at least one of these three variables is false. They are not all in the true bucket. Using logical notation, I'm going to say if at least one of them is true, XA or XB or XC. Okay, this is the logical OR. Okay. And at least one of them is false. So this is our usual convention for writing false. You put a bar on top to say is the negated value. XA bar or XB bar or XC bar. And in fact, we will even, the OR is usually written like this. So for every Pythagorean triple ABC, I have these two constraints. And both these constraints look like this. They have exactly three variables in them. Either all three variables are positive or all three variables are negative, and you're just putting them together in an OR. So when we put together variables like this in an OR, this is exactly what we call a clause. Right? This is also something that you have seen. This is one clause, this is another clause. Every Pythagorean triple is giving rise to two clauses. You're looking at numbers 1 to 7, 8 to 5. There are less than 10,000 Pythagorean triples up to there, 9,000 something. Double that many clauses. So how many clauses do we have? We have 18,000 clauses, roughly. Okay. Okay. So now this is the instance of SAT. Okay. So is the collection of clauses XA or XB or XC, XA bar or XB bar or XC bar 1 less than A less than B less than C less than or equal to N simultaneously satisfiable? Is there a way of assigning true false values to the variables x1 to xn such that all these constraints are simultaneously satisfied? And now, as you mentioned, there is a, if you look at the author's web page, you will find a coloring of the numbers. And that coloring has more than two colors. We are only talking about true, false, red, blue. You want to put all the numbers in two buckets, red and blue. So what they have is a very nice pictorial description. Here are the numbers 1 to, well, 0 to 100 to 200 or whatever. And then here you have numbers 1 to 99. So at this position, you will have the color of 0 to 99, then 1 plus 1 to 99, 2 plus 1 to 99. You put the color of that, of I plus j here, okay, in the location ij. And their coloring, if you look at their page, has red, blue and white. It's not just red, blue. Why is that so? So their coloring has three colors for numbers which are less than 7825. Because for 7825, there is no good coloring. Okay? So for n less than or equal to 7824, they show colorings with red, blue and white. And the white simply means that it does not matter in which bin you put that number. It does not interfere with a Pythagorean triple belonging to a bucket or no. So they have a whole lot of whites in their colored square, but most of the numbers are red or blue. They are rigidly in one set or the other. So this is the question that we are addressing. given a bunch of variables, you're given a bunch of clauses. In this case, the clauses are all 3 clauses, but in general, in SAT, the clauses could be of any size. They could have some positive, some negative literals here. Here it turns out that all the clauses are completely positive or completely negative. But a general SAT instance could have variables appearing in clauses in all kinds of forms. And what we want to know is, can the clauses be satisfied simultaneously? A SAT solver is trying to solve this question. So what a SAT solver would do, it would take as input a formula like this, a formula which is a collection of clauses. And what do you think it will give out as an output? A general SAT solver on a general formula. Of course, it should say yes, it is satisfiable, or no, it is not satisfiable. But a solver worth its salt has to give more information than that, no? If it says yes, you're not going to believe it. If it just says no, you're not going to believe it. So if it says yes, what is the least that you expect it to do? Give the assignment. Give the assignment, right? Yeah. So either it gives yes, and then it gives an assignment. So let's say it gives a A1 to AN. No? If there are n variables, then it gives this assignment. And then the verifier can just plug in that assignment and check that all the clauses are satisfied. Or the SAT solver will say no, and then in some form it should give a proof that there is no satisfying assignment. 200 terabytes is for that particular question. But in general, it could be, it could be smaller, it could be bigger. Okay, so proof that F is really unsatisfiable. So what do we expect from this proof? The proof should be something that is easily mechanically checkable. Okay? That 200 terabyte proof satisfied this, but in general, also for other formulas, if it says yes, then the proof is indeed checkable. The proof is that assignment A1 to AN. If it says no, I expect the no proof also to be easily checkable. Okay. So this is what we want a SAT solver to do. Do you think there are efficient SAT solvers? You just heard already an hour ago that SAT is NP complete.
Solvers that use heuristics.
Yes.
Nice heuristics to figure out whether they can exist or not.
So are they efficient?
Yes.
How efficient?
They will terminate after some time.
Well, even a non-efficient algorithm will terminate after some time. A brute force algorithm which tries out all assignments will terminate.
No, it has a predetermined termination. Right?
Who determines it?
The creator of it.
The creator of the algorithm determines it? Well, so if the algorithm is forced to terminate at a time when it still hasn't figured out the answer, then it is going to give one more type of answer. It's going to say, yes, here is the assignment, or no, the formula is not assigned, or it will say, I don't get no, I need more time. If you give it a timeout, it may end up doing that, right? We have to be careful about that. But you're absolutely right. There are a whole lot of heuristics which will allow you to try and solve this a little bit better than brute force. So one algorithm which very clearly solves this satisfiability question is a brute force algorithm. What is the simplest brute force algorithm you can think of? Try everything, okay? So one brute force algorithm would be try out all assignments. Okay, so if we do this, then you can see that on yes instances, the proof would be the assignment that is found, and you don't know whether you're lucky and you find it early on or whether you're unlucky and it comes much later. But if the answer is no, the proof is always going to be of length 2 raised to n. There is no shortcut proof in this case. Okay? So clearly this is not the brute force algorithm that those guys did, because for no instances, there is no shorter proof in this case. Here's another essentially brute force algorithm. And this is a backtracking algorithm. To understand why I'm even calling this brute force, maybe it's best to do this via an example. Okay, so let's look at here is a bunch of clauses I have: x or z, y or z bar, x. I hope I write this correctly, otherwise we'll all get stuck. Okay, I need to give numbers to these, so let's make this 1 and 2 so that I can, clause number 1, 2, 3, 4. Okay, good. Okay, so now I want to implement a backtracking algorithm. I start with x. And I say, let me try out x equals 0. Okay, okay, that on this side, then next I'm going to try y. And so I'm saying y equals 0. Then I try z, z equals 0. And then I say, oops, this is not going to work because clause number 1 has been falsified here. By the time I try x equals 0 and z equals 0, clause, so this does not work. Okay, so maybe I should try z equals 1. This also does not work because clause number 2 is falsified. Y or z bar. So a backtracking algorithm will say, I tried this, z, both options did not work, so you have to go here and try the other option for y. So you try y equals 1. And then at this point, you're not obliged to try z again. Maybe, you'll try u. Why not? So a backtracking algorithm, I'm not saying that you must try out the variables in a specific order. So let's try u. Let's see what happens now. So if I try u equals 0, clause 4. No, clause 4 is satisfied. What is falsified? 3 is falsified. Okay. False things we should, okay. Red marks. Okay. What about u equals 1? Now 4 is falsified. Okay. So now you backtrack. What happens when you backtrack at this point? You have to go all the way here. This is the usual backtracking. Okay. So we try x equals 1 and then let's try out u here. U equals 0. Let's try v here. V equals 0. Something fails. 5. Okay, if I try v equals 1, 6. Now you can see I've even numbered the clauses so that they fail in order 1, 2, 3, 4. Well, they fail in that order because the variables I'm trying in a certain order. If I tried with the same clauses, if I tried the variables in a different order, this would change. Okay. So what do I do here so that I get 7 and 8 nicely? Let's try out w. W equals 0 and w equals 1. Good. 7 will fail here, 8 will fail here. This is a backtracking algorithm. But is it a brute force algorithm? It's essentially brute force, no? It's optimized brute force, exactly. It's pruning the search in a certain way, which is that here the number of variables was, so I have only 8 leaves here. That's like 2 raised to 3, but there are more than 3 variables there. So at this point, for instance, where we reached this clause is falsified, we pruned out how many assignments? All the extensions of the assignment x equals 0, y equals 0, z equals 0, all extensions of these with whatever value you give to u and to w and to v, at one shot they were all taken away, right? So this single leaf was responsible for eliminating 2 raised to 3 assignments. And in fact, each of these leaves is eliminating those many assignments. 3 of the variables are fixed and another 3 are free. So this is a brute force in some sense, but it is definitely much better than a very dumb brute force. You can see that the size of the proof, this is a formula which is unsatisfiable, but the size of the proof is manageable. So brute force proofs also can be manageable if the brute force is done well. What do we mean by done well? What happened in this case was that, on each branch within 3 levels, we hit a clause or a constraint which was falsified. That may not always be the case. So what does that depend on? It depends on the choice. So here I said I will branch on u, whereas here I chose to branch on y. Does this make a difference? Which variable do you branch on? So it actually makes a huge difference. This algorithm, the way I describe it, is the first SAT solving algorithm. This is from the 50s. And this is commonly referred to as the DPLL algorithm, which is a merger of 2 different algorithms. There's a Davis-Putnam algorithm and there's a Davis-Lagemann and Loveland algorithm. But basically, it's a kind of backtracking and Davis, this year started on a bad note. Davis died earlier on Jan 3rd or something like that. It is the same Davis, yes. So the ingenuity in this algorithm, if at all, is in choosing the variables to branch on. Which variable am I going to check now? Which variable am I going to check here? Which variable should I check here? And there is no foolproof method of choosing this variable which will allow you to terminate in polynomial time. Well, Okay, I should correct that. There is no known foolproof method. Maybe there is one, but we don't know. Okay? So we use some ingenuity. These are the heuristics. And if we are lucky, they will lead us to a solution quickly. For many practical instances of satisfiability that arise in many applications, this was good enough, but there were a huge number of applications for which this was simply not enough. The DPLL algorithms, they have some nice structure, they are very easy to implement, but they were simply not fast enough for many industrial style instances. So therefore, you need to do something more. And this was certainly not the algorithm that was used to solve the Pythagorean triple problem. So what is the next kind of algorithm? So the big breakthrough. So it's called a SAT revolution. So this DPLL style algorithms, these are from the, Suresh should know better, is it 50s, 60s? I think 60s. 60s, right? Yeah. Before all of you were born, before I was born also probably. I was born somewhere in the 60s. The DPLL algorithm is from then. But a SAT revolution which really made SAT solving very fast. There is this, you heard at the beginning of today's val function, Venkatesh saying that there is this disconnect between practice and theory. Practice sometimes ahead of theory. Theory says satisfiability is NP complete. There is virtually no hope of a polynomial time algorithm. Practice tells us if your problem can be reduced to SAT, you're in good shape, it's done, let's move on to harder problems. And that revolution came here in the 90s. So this is now an algorithm which is not brute force. It's very actively doing something beyond brute force. So this is what is called the CDCL style algorithm. Okay. It's not one algorithm, it's an algorithm style, a template, so to say, for solving satisfiability instances. There are three major ingredients in these kind of algorithms. I'll describe those ingredients and we will look at one example. I think that should be better. So what are these three ingredients? The first ingredient is what I would call Boolean constraint propagation. Which seems a bit of an overkill. I mean, we are in the Boolean world anyway. So Boolean and constraints, of course. So maybe more commonly it's called unit propagation. And what this unit propagation means, you can go back to this example and say, okay, at the first step you decided that you will set the value of x, try out a value of x. You decided that you will first try out x equals 0. In this example, it didn't matter which we tried because both sides were roughly the same, but sometimes it even matters, will you try out x equals 0 first or x equals 1 first? Let's say we decided to try out x equals 0. Then we went on to try out some more things. But if you just stare at the clauses here, the moment you set x equals 0, clause 1 tells you if you have any hope of finding a satisfying assignment, you had better set z to 1. That is what I call a Boolean constraint propagation. The setting of x to 0 propagates the value of z to be 1. Okay? And a value gets propagated only if a clause becomes, because of the assignment so far, it shrinks to a unit. A unit is something which has just one literal in it. So that the first clause has two variables in it, x or z. But once I set x to be false, it has only one variable left. The other variable has died. Okay? Whereas if you look at clause 6, you set x equals 0, it does not become unit, it becomes true. Because you have set x equals 0, clause 6 is satisfied. It is no longer a constraint. But clause 1 becomes unit. The moment a clause becomes unit, you can propagate that value. And this is such a simple idea. Of course, you should propagate values. No? I mean, if you're, it's the same, it's part of optimized backtrack. So I was not completely fair when I said that DPLL algorithm is basically this. The DPLL algorithm was a combination of DP and DLL, and the two of them together, they did do Boolean constraint propagation. You choose a value to decide, a variable to decide, and then you propagate whatever results from that before you do further branching. Okay? So this is something which is there in all CDCL algorithms as well, but it came from the earlier DPLL algorithms. Modern SAT solvers, about 99% of the time that they spend is on doing unit propagation. Well, maybe not strictly speaking time, it might be maybe 99% of the assignments that they try out, that they make in modern SAT solvers are unit propagation. And this tells you, you're spending so much time on unit propagation, so it really matters which variable you choose to branch on, right? Because that is what dictates how quickly you reach unit propagation. So this is the variable decision, that is which variable to decide, as well as the value, whether to choose it to be true or false. You need some heuristic to decide this. Okay? Of all the variables which are sitting out there, which one do you choose? Initially, maybe it's like a shot in the dark. You pick something randomly. But as the algorithm proceeds, there should be other information which you can use. For instance, there is one heuristic which is used very commonly, which is something called, let me see if I can recollect it's called VSIDS. What does VSIDS stand for? I think it's something like this: variable state independent decaying sum. Yeah. Okay. Here is one heuristic which is used in almost all solvers today. And what does this do? It says reward variables that have participated more recently in conflicts. So what do I mean by a conflict? A leaf like this is a conflict. You reach there and then you find, oh, some clause cannot be satisfied. This is like a bad state to be in. That's a conflict. So if a variable participates in reaching a conflict, then you reward it. So it is more likely to be picked as the next variable on which you will branch. So for instance, in this example, on this branch, x equals 0, y equals 0, z equals 0, y did not participate in the conflict. We finally reached this conflict here, and the conflict was x or z. Y did not participate. So at some stage, we will try and remember this, that y did not participate in a conflict and x and z did, and the x and z get preference over y. So in such a small example, it does not show up, but in bigger examples, this can play a big role. Okay? So you reward variables that have participated more recently, and you do some kind of damping. Damping you apply uniformly to all variables. So you try to kind of attach a score to every variable, whether it participated in a conflict or no, and then uniformly multiply everything by half or 3/4. So if something has participated in conflicts but very long ago, again it loses its advantage. It's not clear. Is there science to this? This is a heuristic, but it seems to work. Right? So it's a trick. It's a good trick, and it seems to work in practice. So this is the first ingredient that CDCL algorithms use. Well, DPLL algorithms also used. Let's look at the second ingredient. And the second ingredient is in fact what is giving us the name, CDCL. I have not yet told you what CDCL stands for. By now some of you have already looked at it. Do a conflict analysis. This is something that the DPLL algorithms did not do. You try out some assignments, you try out some values to variables, then you reach, oops, I'm stuck. Some clause is satisfied, so you backtrack. These algorithms say you don't just backtrack. You also analyze, like, why do you need to backtrack? Some clause was not satisfied. Okay, what clause was that? Can I learn something more out of that clause? Out of the fact that something was falsified. Now, what do you mean, can you learn something more? You can learn that you cannot make the assignments along this path. Okay? So, going back to this example, of course, you can learn that you should not set x equals 0, y equals 0, z equals 0. But that you knew anyway because of clause 1. So what we really want to know is, can you learn something new which was not already there in your initial formula? And this seems very strange. After all your propagation is being done using the existing clauses. How can you learn anything new? So what we need to remember is that when I say let's learn something new, it's not that we are learning something which is totally new. We are learning something which was implicit, hidden in the constraints, and now you want to make it explicit. So this is something which I would like to give an example for, but let me just complete this. So what conflict analysis does is it helps us to prune an even larger space. Already backtracking, the way we optimized it, you are pruning away large parts of the space. Conflict analysis does even more. So the CDCL stands for conflict-driven clause learning. Every time you reach a conflict, you somehow analyze the conflict, and I will show you an example of that. And from that analysis, you learn a new clause which was not there in your initial formula. It's a clause which was not there, but that clause has the following property. If at all your original formula was satisfiable, if at all there was an assignment that satisfied that original formula, that same assignment would also satisfy this clause. So adding this clause to your existing formula does not change the status of is it satisfiable or no. Right? It has exactly the same property, the formula without this clause and the formula with this clause. So you can add it to the formula. But then if it has exactly the same property, what do you gain by adding a clause? What could you possibly gain? Why? You may not have to look at so many variables if you add clauses. If you remember, 99% of the time was being spent on unit propagation. The more clauses you have, the more unit propagations get enabled. You will be able to more quickly reach leaves of this tree without branching. You want to reach leaves without branching. Branching takes more time. Right? You're branching, you have to try out both sides. Unit propagation, you try out only one side because the other side you know is ruled out. When you have more clauses, more unit propagations are likely to be enabled, and so you will reach conflicts faster. So we add clauses which are anyway implied by the given clauses, so they don't change the status of satisfiability, but hopefully they will allow us to reach conflict faster and so prune out large spaces faster. Right? So that's what we want to do. We want to learn clauses smartly by doing this conflict analysis. So the reason why it allows you to prune a larger space and more quickly is that in contrast to a DPLL type algorithm, when you learn a new clause, you don't just backtrack. You're able to back jump. Let's go back to this example. At this point, even without any clause learning, at this point, X or Z, so if we had tried Z earlier than Y, then we would have immediately gone over to the other side. And this is independent of the value of Y. Now, somehow you want to say that this is happening at a more critical level so that a large part of the tree vanishes. This example does not show it. So we need to go to another example to illustrate that. So what this is going to allow us is to back jump. You try out something, you are here, you reach a conflict, and backtracking would say go one level up. But this conflict analysis allows you at this point to go 4 levels up, 3 levels up, and eliminate a whole part of the tree in this way. Okay? So in order to do this, we need a learning scheme. So this is again another heuristic. When you do the analysis, it tells you what new clauses you can learn, and maybe there is more than one new clause that could be learnt at that point. Which one do you pick? Do you add them all? Then it's a bit dicey. I mean, you could add them all also, because the idea is that when you add more clauses, you have more unit propagations, but then you might shoot yourself in the foot by, there are more things to take care of. So it's not an unmixed blessing. You know? So there are again some heuristic algorithms, heuristics to decide which clauses should be added and which should be not. So the last heuristic I will just write here, not spend too much time on it. There is something called a reset heuristic, which says that periodically while you're doing this backtrack and you have learned some clauses, instead of back jumping, you just give up on this trail and start again from the beginning. You erase the history that you have till now and go back to the beginning. Don't erase the learned clauses. Keep the learned clauses, but don't backtrack in your current tree. Don't just back jump. Go all the way to the top. And this is, in fact, pretty hard to justify. Like saying, why do you want to go all the way back when perhaps you have made some progress? Maybe it's just that you might be stuck in a part of the assignment tree which is unsatisfiable. Periodically, you jump up and end up trying another part where you quickly find a satisfying assignment. So this is useful if your formula is actually satisfiable to begin with. Okay? So periodically, you reset the whole algorithm, keeping the new learned clauses, but throwing away the tree that you have constructed so far. Okay, so I think to make sense of this, we should look at CDCL in action. So just as we saw DPLL in action on one particular formula, let me write down another formula here, because that formula was not good for CDCL. So let's, I mean, it does not illustrate the features. So here's another formula. Okay, I think we are going to need more clauses to illustrate the features of CDCL, but we can do this. Okay, so let's say this is our formula, 9 clauses. They are not all 2 clauses, some are 2 clauses, some are 3 clauses, and they are mixed, some positive, some negative, all that is happening. Now, I start with, so I'm not going to draw it like a tree. Now I'm going to draw it in a different format, okay? So let me start by, somehow I decide, okay, P is the first variable that I will set, and I'm going to try out P equals 0. Nobody told me to do this. This didn't come out of unit propagation. This was a choice that the algorithm made. So let's mark that by saying that this was a decision. It was not something which was forced. It was a decision. As a result of this decision, what happens? The moment you set P equals 0, now you know that you had better set U to be equal to 0. This is unit propagation from clause 1. So let's write it here. Clause 1 is the clause which is responsible for telling us that U should be set to 0. If we choose P to 0, then U should be set to 0. Is there any other unit propagation happening as a result? No more. Okay, let's make one more decision. Okay, let me decide to set, oops, I got a color wrong. Let's set Q to 0. Again, this is a decision. Does this enable any? R equals 1. This is from which clause? Clause 2. Okay. Then it also makes W equal to 1 because of clause 3. So I made one decision, it propagated 2 unit propagation, 2 BCP steps, Boolean constraint propagations. Anything more? I don't think anything comes out of this. So let's go back to a decision. Okay, let me set X to 0. Okay, this is a decision. What happens as a result of this? X is set to 0. Look at clause 4. X is 0 and U has already been set to 0, so Y should be set to 1. And now Y has been set to 1. Look at clause 7. This tells you that so Z can be set in many ways. So let's say Z should be set to 1 because of clause 5. Because X was 0 and Y was 1. But Z should also be set to 0 because of clause 7. Right? So this is a conflict. Okay. Now if you think of the DPLL style algorithm, what would it do at this point? It would backtrack. It would say, oh, so now I should try X equals 1. The last decision you made was X equals 0. That's wrong. We won't just we will backtrack, but we will do a little bit more. We'll say, okay, why did this conflict come about? This conflict came about because there was this clause 7 and clause 5. So let's look at clause 7 and clause 5. Clause 7 is saying that at least one of Y and Z should be false. Clause 5 is saying either Y is false or one of X or Z is true. If I combine these two together and you stare at it a bit, you can convince yourself that in fact this clause must be true. If you have an assignment which is satisfying both 5 and 7, could it be satisfying both 5 and 7 because of Z? No. Because Z is appearing in opposite ways in these two clauses. No? So if an assignment is satisfying both of them, at least one of those two is satisfied not because of Z, but because of the rest. And then that part, because of the rest, is appearing here in X or Y bar. So this will also be satisfied. So if there is any hope of satisfying both 5 and 7, then that would also satisfy this clause. So let's introduce this clause and give it a number. We have up to clause 9, so let's call this clause 10. This is a clause which was not there in my original formula. It's a new clause, I can learn it. Okay. I can learn this clause. Now, 4 led to 5, so maybe I can also learn something from these two. Any assignment, so where did 4 come from? 4 came from U or X or Y, and here I have X or Y bar. So from this I can conclude U or X. This is clause number 11. Again, this is a clause which was not there in my initial formula. But if an assignment satisfies the original formula, it must satisfy clause 4, it must satisfy clause 10, then it will have to satisfy this. So throwing in this formula clause into the formula does not change satisfiability, but is going to be useful for us because now, where? So clause 4 is uxy. And clause 5 will give you ux and z. And here I have got a shorter clause, ux. Now this is again a heuristic. Are shorter clauses better than longer clauses? They should be better because they will more quickly become unit. So you are trying to look for the short clauses. Okay, so here we have u or x. Now, remember I mentioned that there are these learning scheme heuristics. So here's a learning, there are these two clauses that I can learn. Maybe if I analyze the conflict further, there are even more. A scheme will tell me which clause to pick. So let's say that I choose to pick this clause, u or x. And I'm going to add this to my formula. Now, where will my backtracking take me? Now it's not backtracking, but back jumping. If I add this clause to my formula and you start looking at this, okay, I decide p equals 0 as before. This was a decision. That propagates u equals 0. And that immediately propagates x equals 1 from clause 11. Right? The fact that I learned this clause means that I back jump here, as opposed to back jumping just to one decision level above. So I can go up there. That's good news. And then you can continue. So this is the kind of back jumping that happens. And in the interest of time, I think I should stop here with this example. But you can continue this example, and in another 3 more trails you will find, in another 3-4 more such paths, you will find that you end up learning. Here remember I said from these two clauses you can learn this clause. From these two clauses you can learn. Suppose at some point you end up learning a clause which is empty. I have already derived, let's say, x here, and I have derived x bar here. Any assignment which satisfies both of these must satisfy the clause which has no literals in it. But you know there is no such assignment, no? So this would be a proof that the formula is unsatisfiable. This is my CDCL algorithm. It makes decisions, propagates units. When it reaches conflicts, it analyzes those conflicts, learns new clauses. At any point, if it finds that all clauses are satisfied, it's done. Formula is satisfiable. At any point, if it finds that it can learn the empty clause, it is done. It has a proof in this format that the formula is unsatisfiable. So a run of the algorithm produces a proof. And what does the proof look like? The proof looks like this. Take clause 7 and 5 and combine them. Then take clause 4 and combine it with this. Take something else, take clause 6 and clause, and eventually derive the empty clause. That would be a proof. Now, can you see that a proof of this form should be very easy for a machine to check? It does not require any ingenuity. What do you need? You need a data structure that can represent the clauses, tell you what are the variables in the clauses, positive or negative, and just check off that the right variables are represented. So this is how a typical CDCL algorithm runs. And what is it that they can achieve? Okay. So today, CDCL based solvers can handle instances with how many variables? We saw that it could handle 10,000 variables, but it produced a 200 terabyte proof. Well, that was a particularly bad example, but in many, many industrial examples, these solvers can actually handle millions of variables. Okay? They really can. And there are SAT contests. I mean, you are going in for the informatics Olympiad, right? There are exactly like this Olympiad, there are SAT contests, there are people writing SAT solvers, and those are being tested on benchmarks with computers which have a limited amount of storage, limited amount of time, and the results are announced every year at the SAT conference. It's pretty much the same format as what you are doing. What are the other kinds of heuristics and tricks that these solvers are using? Heuristics and tricks. So we already saw the places where you need heuristics, decisions, which variable to pick to branch on, what value to choose for that. So there's the decision heuristic, which variable to pick. There is the learning scheme, which clause to learn. There is also the restart heuristic, which we didn't spend much time on, but when to jump back. Sometimes back jumping all the way is actually useful. Tricks, these are the data structures tricks, which you have implemented often enough. Should I, even in an example like this, or maybe this is a better, the next slide would be a better example. So what could happen in this example, it does not show up, but what could happen is that you make a decision, and as a result, 2 clauses become unit. 2 different clauses become unit. Here it did not happen anywhere, but it could happen. So now you know that you're doing unit propagation, both of those should be propagated. You propagate one of them first, it triggers off some more propagations. Then you propagate the second one, it triggers off some more. Okay, so these two were both propagated from one step. Do you put them in a stack or in a queue? Will this make a difference? You decide X, it propagates Y and Z. Now, if you put them in a stack, you will first propagate Y, and as a result, PQRS also get propagated, and fatak, you reach a conflict. You put them in a queue, you'll propagate Y, then you'll propagate Z. You may delay some things. So just the difference between a stack and a queue, just implementing this idea, can make a difference. And again, there are heuristics to tell you when is it advantageous to use a queue. That's one trick that many solvers are using today. Another trick that they are using is you want to speed up unit propagation. Okay? So, okay, here stack versus queue is one thing. Speed up BCP. Instead of after every decision going through your entire list of clauses to figure out has something become unit, that will take time. We are dealing with formulas which have thousands of clauses. So you have something called a watched literal. For every clause, you keep track of one or two variables in that clause and check. If those get set, then you should start paying attention. This clause is on the verge of becoming unit. Today, there are no modern solvers which don't keep track of watched literals. It's just a heuristic idea, but it seems to make the difference between efficiently solvable and not. There are more tricks like this. There's one more trick, which is occasionally you simply forget some of the learned clauses. Forgetting some learned clauses. Because if you have too many clauses, then again that can slow down your Boolean constraint propagation. So you never forget clauses from your original formula, but some of the learned ones, at some point you just decide, I think this is not going to be useful, let me check it out. You may be wrong, you hope that you are right. So modern solvers do all various combinations of this, and depending on which trick they use and which they don't, they will be good on some instances and bad on some others. So there's a whole zoo of solvers out there. If you're interested in this kind of thing, just look for SAT solvers implementations and you will find a whole lot of stuff out there. Okay, so at this point I'll stop. I'm happy to take questions now or over chai, whatever.